Every day, the future's getting closer.
Welcome to Master the NEC, where we talk about the National Electrical Code and all things electrically related. My name is Paul Abernathy, your host, and welcome to today's podcast. Well, hey everybody, welcome to another episode of Master the NEC, where we talk about the National Electrical Code and all things electrically related. My name's Paul Abernathy, your host as always, and on today's podcast, and hopefully we're going to grasp this okay without any visuals here, is that we're going to be talking about hazardous locations, Article 500, 501, 502, things like that. And I don't know how deep we're going to go into it because I want to keep it short, but I think that the next couple of series of podcasts over the next week or two or whatever, I'm going to devote to the topic of Chapter 5, Article 500, which is going to give you your general scope of the hazardous locations, Class 1, Class 2, Class 3, and then Division 1, Division 2. We probably won't talk as much about Article 505, which is the zone classifications, 0, Zone 1, Zone 2, and then, of course, then with dust, it's Zone 20, 21, and 22. I don't know how much I'll go into that. I might go into that. It's not a code change podcast that we're going to do in these series, and I'm going to do some videos because I've had a lot of requests for people that have asked me to do some hazardous location stuff, so I'm going to do it and talk about all kinds of hazardous location topics. I by no means consider myself an expert when it comes to hazardous locations. I follow the code like anybody else, but we'll talk about those different topics as we move through the podcast and different things that come up. So what we're going to try to learn today is kind of how we categorize, I guess you would say, or label certain areas as a classified versus something that be unclassified. We're kind of going to talk a little bit about labels and the markings and the regulations and the agencies that are associated with dealing with hazardous locations. And we'll try to put it together, and I'll try to give you a visual of some common things you might see on a label or something if you're looking for it. Okay, but what we're really going to focus on here in the podcast is why do we really classify certain areas as hazardous locations? We'll look at some definitions of hazardous locations. If you're following along in the code, obviously we're going to start in Article 500. Article 500 really encompasses 500 through 504. But if you really want to learn the different concepts of what's a Class 1 Division 1 versus a Class 1 Division 2, all that, then you really need to start in Chapter 5, Article 500. And then when you're moving into gas and vapors and specifics as far as installation, seal-offs, and things like that, then you can move into 501. If we're looking at dust, then you can move into 502, and then, of course, filings and fibers and things like that. You would see in 503. So we'll kind of look at the definitions of the hazardous locations, kind of talk about them a little bit, do our 10,000 foot view of that, if you will. We'll look at classifications. We'll try to break down, divisions, the areas, and various classes so that you have a better understanding of what we're talking about when we talk about it as we go further on. So this is going to be more of the introduction into this podcast series when it talks about hazardous locations, okay? And for those that are visual learners, we will be doing a video series on it. It's just much easier for me to pump out podcasts than it is for me to do videos. It takes time to do videos and put the material together. And a lot of times with podcasts, it's just raw me sitting here in front of the mic in my studio and just simply talking code and talking different aspects of it. So think of today's podcast as your introduction, and it's going to serve us well even when we do the video series to kind of get these basics down so that we can spend more time in the installation applications of these locations than actually the basic root of what the definition is of these locations, okay? We'll talk a little bit about markings and specifications, and then we'll talk about the different methods of protection and that are associated with that, okay? Now, when I think of a hazardous location, and if I'm the engineer or I'm whatever is designing this location, I got to look at a lot of things. But what's the reason that we classify locations? Now, obviously, when we classify a location as a hazardous location, we know that there is a potential for an explosion. I mean, that's the whole thing, right? Whether it's gases or vapors, whether it's dust, whether or not it's fiber and flyings, if there's this potential for something like a flammable liquid-produced vapor, combustible liquid-produced vapors, combustible dusts, or ignitable filings and flyings and fibers, we're worried about explosion, right? That's what we're really worried about. Now, some divisions or even zone systems that they use in Europe are going to be specific for certain applications, certain environments, whereas in your Class 1 Division 1, for example, we're really keen on explosion. And in Class 1 Division 2, there's still that explosion risk, but it's usually they're contained in storage, and we'll look at all that. But what are we doing all this for? Well, first of all, we really are doing this. Article 500, 501, 502, 503, 504, for example. And of course, the same thing applies to 511 and all this type of stuff, or 516 for spray booth. We're trying to protect personnel, right? I mean, that's what we're trying to do, right? Trying to protect people. Now, we're also trying to protect property because, again, economics-wise, if you look at the scope of the National Electrical Code, I mean, persons against the hazards that are associated with electricity. But, we're also out there and trying to protect property. Sometimes these things, you can have consequences. If you have a petrochemical plant, and obviously that'd be a Class 1 Division 1 location more often than not in the areas where we're going to be significantly talking about today. Not only do you have the potential for an explosion to hurt personnel, but you could have a catastrophic event that is basically domino effect to other parts of the property that can also affect people, but also affect the equipment. And again, whether we like it or not, you have a petrochemical facility and you protect your people, but you blow up the facility and you have these safeguards that you can put in place. Then it affects the economy. It affects a lot of things, especially if it's tied to the gas producing, oil, refineries, things like that. So the whole process of hazardous locations, one is to protect personnel, and also it is an effort to protect property from this application of potential explosion. Now, we all probably have heard about this triangle scenario, whereas you have to have these three elements in order to create that explosion. So you have to have an ignition source. Now, in a hazardous location, an ignition source could be an open flame as part of the process. I guess it could be a temperature rise, a heat rise to get to a certain level that it gets to what we would call an auto ignition, or it gets to a liquid that gets to a certain flash point. Those type of things based in that location. It could be a spark, a make or break, or something that's in this location, something that's going to produce an ignition source, right? And that is your one element of the triangle, for example. The next thing you need is an oxidizer. And typically what we talk about is what is the predominant oxidizer in our scenario, and that is oxygen. And there's oxygen everywhere. So you have the oxygen present, and you have the ignition source present. What's the last component that you need in order to create this explosion, this volatile situation? And that's a flammable substance, whether it's flammable gas, something like maybe a hydrogen, which is flammable, and maybe there's flammable liquids or vapors present for whatever it might be. I guess it'd be things like acetone, kerosene, gasoline, things like that, flammable liquids. That can produce flammable vapors as well. Of course, you could have flammable solids. I mean, that's what we're talking about in a Class 2, for example. You could have dust and fibers, and like in a Class 3. All of these things could be there and facilitate an explosion. If all three of these things together are put in a perfect environment, then you can have a situation where you could have an explosion. And again, you could hurt personnel, people, your workers, as well as affect property. And it could be multi-million dollars equipment that can not only save people, that's the first thing, but also it could be devastating economically to the company when there are things that you could put in place to help minimize the risk. Now, what type of locations are we talking about here when we're talking about hazardous locations? I mean, I guess the engineer is going to specify it, the plans are going to show it, but the places could be endless. Paint shop, paint booths, notorious for vapors, corn and flour mills, coke plants, All of those produce the dusts that can be extremely hazardous and flammable. Refineries. Down in Houston, there's a lot of refineries, oil refineries, crude refineries. All of these locations, there is a lot of classified locations down there. A lot of Division 1 and a lot of Division 2. Typically, Division 2 is adjacent to a Division 1, and it can be communicable between one zone or one division to another. And so you have to seal offs and things like that, which we will talk about in another podcast about seal offs and how they're to be done and all this kind of stuff, and the difference between Class 1, Division 1 and 2, and Class 2, Division 1 and 2, and that type of thing. And even as far as when we talk about zones, again, Zone 0, 1, and 2, and then for dust, you got Zone 20, 21, and 22. And we'll talk about all those type of things as we go through this series, because I'm going to do more on this series. So you got those refineries, obviously, can be an explosive environment. What about chemical plants? Most certainly chemical plants, some of them that produce medical-grade chemicals, drug plants, a lot of those type of things. Chemicals, Dow, DuPont. Can be certain types of areas in a facility that can be labeled as a Class 1 Division 1 or Class 1 Division 2. There's also, you can have inside of facilities where you might have a facility that's considered unclassified, and then all of a sudden within it you might have a location that is considered classified. It might be Class 1 Division 1 or Class 1 Division 2, depending on what's going on in there. And we'll talk about the classes, or the divisions and stuff. But chemical plants are notorious for this. Again, part of their production. And it can be really different. For example, there could be an area in the chemical plant that at any given time you could have something in the air that could be explosion of flammable gases or liquids or vapors, always part of the production process, or certain types of combustible dust that are always part of the process. And then you might have other areas in the facility that it would only happen under an accident, and that it's usually contained, and it would really take a catastrophe, a breakdown, in order to contaminate the area. And so that might be a difference between Class 1 Division 1 and a Class 1 Division 2, even though both of those types of mixtures could be there. Just one is there in concentrations that is expected, and one wouldn't be unless there was some kind of breakdown or something like that. So you'll talk about that more as we move through the series, but I'm just kind of giving you that 30,000-foot view of understanding these hazardous locations. How about liquid transfer terminals? Again, if I'm having stuff come off, like barrels of crude come off of a ship, and you're moving it from one ship to the port, or from one location to another, or maybe even from train to a certain area, you could have certain transportation areas or movement areas between these transfer points that could be a hazardous location, and something you have to look at. Maybe it's just Class 1 Division 2 because it's generally everything's in storage containers, or there's some kind of transmission, a physical movement from a tanker, let's say, into a certain area, and then you've got a movement of liquids, for example, and then of course that could end up being the area that you're working in, could end up being a Class 1 Division 1. So we have to look at that aspect of that. Of course, there's all kinds of holding tanks, a lot of them down in Houston area, a lot of them around Oklahoma, that will store material. And then, of course, you've got to be worried about the material that's being stored in the area around those, especially because there's a lot of times transfer of those fluids or whatever through tank to tank. So whether it's going to be transported or stored. And so you could have some locations that explosions could occur. And we got to think about the ratings of those locations, okay? Now, we all know that explosion is the issue. That's what we're worried about. But there are ways that we can prevent explosions, okay? With things that we know we can do, okay? Now, one thing is we can have an area, let's say it's Class 1 Division 1, and we require explosion-proof enclosures, for example. And they're designed to contain the explosion. Okay, they're not going to stop the explosion. They're designed to contain it within itself. And that's why it's so important to understand seal-offs, okay, and why we have certain rules for seal-offs. And we'll talk about seals. I'll talk about it within 18 inches. We'll talk about boundaries and within 10 feet of boundaries from a Class 1 Division 1 to a Class 1 Division 2. We'll talk about all that later. I can't give you everything in one podcast. But just understand that when you get enclosures and they're explosion proof, the explosion could still happen. but it's contained within the device or within the enclosure. Okay, so that's one way of preventing an explosion, but not necessarily preventing it. It's containing it, if you will. Okay, and it's not really designed to sustain that and be operable after that. It's do its job, and that's the whole concept. Okay, and we'll talk about Nema classes and enclosures again as we move through this podcast series. But one thing in a Class 1 Division 1 location, if we're going to have enclosures and they're explosion proof, then they're going to actually contain any type of internal explosion. For example, if I have something that generates a spark or an arc, and it's going to be inside of an explosion-proof enclosure, then and if there's a device in there that could generate that spark, then it typically is going to be in an explosion-proof enclosure, so that if it was to have the ingress of any potential gases or vapors, that if it were to come in contact with that arc, that it would contain it within the enclosure. Okay, and so making sure that you don't damage those enclosures, that they're sealed properly, that there's no nicks between the cover and the actual enclosure itself, the cabinet part of it. All of that has to be done in a certain way that you know that the integrity of that equipment is going to be maintained. So that's why the guys and gals that work in those areas really have to stop and slow down, because any small nick, any small scratch that could allow some gases to escape or get in could be a problem. Okay, so one way to prevent it is contain the explosion with explosion-proof devices and enclosures. That's one way. Now, the other one is simply remove the possibility of a spark or other potential source of ignition. Intrinsically safe means it can't generate enough energy to even produce spark. Okay, so a lot of times when you see the term intrinsically safe, it just doesn't have enough energy to produce a spark. Remember, there's that triangle concept, okay, that we're dealing with here, is that you have to have an ignition source, you have to have an oxidizer, and you have to have a flammable substance. If we can remove any part of that equation, then we can remove the potential for an explosion. So if I can remove the potential for the spark by using something that's intrinsically safe, for example, then I can make it a safe application. And so the code deals with intrinsically safe applications. And so that's one of the things that is important to understanding your scheme of design, and you know what you're working with. Okay, so again, if I can remove the possibility of the spark, and there's other ways to do that too. Okay, I could actually there's applications where I have switching devices or whatever that are immersed in an oil, and they simply cannot. There could be pressurized. There's applications where pressurization could be utilized. Different aspects where I'm keeping that separation in order to remove that potential source of ignition. Okay, and so there's other viable ways to do this, and the manufacturers make plenty of different types of devices and the things that can do this. Okay, and the third way would be isolate the explosive substance. Okay, so if you isolate it away, you take it out of a condition where all these other elements, the other two potentials are there. So in other words, the flammable substance is kept at a distance from the oxygen or from an ignition source. And if you separate these out and you do that in a design scheme, maybe it's piped from point A to point B, and there's something in the process that helps isolate one portion of this explosion triangle that we talk about, then you can literally remove the possibility of explosion. So there's ways to do it. There's schemes to do this. Okay, and everybody that does this, the manufacturers that make the equipment, have various ratings, and the labels will give you all that. And I'll give you some examples of some label information here in a little bit. But that's the kind of thing you're looking for. Now, when I think of guidelines and who's the one that governs all of this about hazardous locations, and it kind of is call across the board here. If you're in Europe, then you have your own requirements and IEC standards. You're in the U.S., you have your own type of standards and regulations. So I'm just going to kind of give it to you from a 1,000-foot view, because there's a bunch of different type of nerdles that deal with this. But the predominant ones we talk about generally is Osha. And of course, OSHA is the one that lists all the nationally recognized testing laboratories and different things like that. You've got the National Electrical Code, which we're talking about today. So we're in Article 500, 501, 502, 503, 504. We have rules in 511 for commercial buildings. The National Electrical Code gives us great information, especially for what's considered a Class 1 Division 2, Class 1 Division 1, and all the other types of classes and division locations, as well as zones. Even though zone is typically an IEC or a European standard, it's making its way into the US. Many people are using it. Why? Because zones break things down a little further. Whereas you have a Class 1, Division 1, Class 1, Division 2. If you go to zones, you'll have a Zone 0, you'll have a Zone 1, and you'll have a Zone 2. 2 being equivalent to like a Class 1, Division 2. And of course, if you're dealing with dust and things like that, then you're going to have an application where you've got a Zone 20, 21, and 22. Same thing. 22 is going to be equivalent to Class 2, Division 2. And so in the Class and Division 1, where you have a 1 and a 2, they're kind of similar, except for, as you see with the IC versions, there's 3 different classifications there, whereas the normal standard that we use NEC, there's 2. There's a Class 1, Division 1, and Division 2. Now, into the zone, 0 and 1 are equivalent to Division 1, and of course, 2 is equivalent to Division 2. And so that's kind of how that works. And the same thing can be said for the combustible dust, as the fact that the Class 1 is equivalent to 20 and 21, and then Class 22 is equivalent to Division 2. Okay, so it just is the zone breaks it down a little more. Okay, gives you one more category to work with. All right, so in North America, we predominantly, at least the lower North America, we use the National Electrical Code. Obviously, Canada, the CEC, have their own rules, and the Canadian Electrical Code. There's a lot of things that have to do with the NFPA. Obviously, the Fire Protection, National Fire Protection Association plays a huge role in certain standards. And in some cases, even insurance requirements are going to dictate what regulation you use, what kind of markings and labels and things like that's on the products. Okay, so now there's a bunch of different types of certifying bodies, if you will. There's, for example, one of the biggest ones that deals with hazardous locations is FM. That's Factory Mutual. If you see the FM mark, now one thing to remember about FM is that FM has a U.S. and a Canadian branch. Okay, so yes, you can get the ones with an FM that also has a C or a U.S. on it, okay, because they do have divisions both. Now, they're a private insurance organization, okay, but they do these testing, okay. They're very popular in the U.S. We see a lot of this on the fire stuff, okay, for transfer switches and things like that, so they're very big. And they actually will test products in order to get their certification, okay, to get their mark, if you will. I'll say it better that way. I'll say they'll get their mark that they'll place on the equipment. So they're a testing body, but they are a private insurance organization that does this. The one that's probably the largest is probably, and I'll say the largest in North America, because Underwriters Laboratory is a private standards testing organization. They're for profit. But they do their testing. They're very popular in the U.S., but they also have an agreement called an interagency agreement with CSA, which is the Canadian Standard Association. So you can get a UL mark on products for use in Canada with the same UL. It's just got a little C beside it. Okay, so and you'll have C or US, and that lets you know that it's interagency agreement. And so you can have it tested for that. And a lot of the manufacturers actually do that. If they want to use their products in Canada, they can use UL in order to get that interagency agreement. Now, of course, they also test products. The company I work for manufactures wire and cable. They're in our facility all the time. They request samples all the time to be sent to their facility in Melville, New York. And we send samples all the time for them to do their own testing on products in order to make sure that we're giving customers the best possible product you can. We're not cheating, cutting any corners on any of the material, catalysts, things like that. So it's quite expensive to do that as a manufacturer, but it's part of a follow-up program. Once you get a product listed, you have to continue to follow up to make sure that you're following the standard. You're continually making the products to your original footprint that you submitted. Okay, so that's what we do. And so that's UL, and they can put their mark. A manufacturer can get that mark on their products for hazardous locations as well. And then, of course, there's the standards for Canada. Canada Standards Association, CSA. That's kind of a government-driven organization. They do test products for approval, so you can submit products. In fact, our facility, we have a couple products that are CSA stamped. Rather than go through a ULC and US, we have some that are just specific. Instead of teaming up with one association, we do have a couple products that have the CSA on it. And it's a government-driven association or organization, I should say, but they do test products. So you have to have those products tested if you want. And they also work very well in Europe, too. So CSA purchased CIRA, SIRA, which kind of does global testing as well for use in Europe, the EU, and things like that. So they've got a big reach as well. So if you go through UL, again, you can get US and Canada. But again, if you go through CSA, then you might be able to get even bigger global reach if that's what you're looking for. Again, we're just talking hazardous location products right now. And as, of course, you saw with UL, that also tells me that CSA has what's called an interagency agreement with UL, so that if you're Canadian products, they can get cross-agency agreement marked for use under UL, okay? So, there you go. Now, outside of North America, there's generally two different types of tracks that you can go. One is the ATEX or ATEX, okay? So that is really used in the EU and other worldwide countries, and that's what they do. It's kind of a harmonized standard that they put out there, and the tests that are performed by notified bodies, and they do their testing. And again, if you want to get your products in the U.S. and you want to get them for use overseas, then ATEX might be one method to go, and you can have your products tested to those harmonized standards by their notified bodies, specific set or group of testing agencies that are actually set up to be ATEX, and then you can get your mark put on your products and you can use it overseas, okay? But the biggest one that you're probably going to see for your products is going to be IEC, and that's the International Electrotechnical Commission. Okay, and their headquarters are in Geneva, and it's widely accepted all through the EU and other world countries. They actually are a direct competitor to ATEX, so you have your choice there. IEC is probably bigger known. They test the same way, but the testing is done by notified bodies. And the IEC, if I was in the U.S. and I wanted to get my product widely used, not only in the U.S., but also to comply with the harmonized standards that are in Europe, which can be different standards, different test criteria, then that's probably the one that I would go with, so that I can have both the FM maybe here, or UL here, or CSA here, but I also have an equivalent IEC testing for use in Europe, so that product has a broader scope. Now, if you're a U.S.-born, a U.S.-based company, then you might not have any need for anything that's in North America, outside of North America, I should say, okay? But if you're a business that doesn't crosses the pond, then you might want to go with the IEC. But ATEX and IEC are both options that you can have if you want to do that. Now, hazardous areas. Let's kind of jump back to hazardous areas, because there's quite a few steps here when we're determining a hazardous area. And there's different ratings, whether it's for equipment, whether it's the temperatures and things like that. So there's generally 6 things that we want to consider. The main scope of the things we want to consider is the area classification. We want to talk about the division in zones and how they relate, because this will all be the things that are on a label, for example. The equipment group. What equipment can go in certain applications under certain conditions, certain gases and vapor, where they're going to be located. There's a lot of things have to do with temperature class. So a lot of the labels for equipment will have temperature class markings or notifications on them. Okay. The other thing is the protection concepts and what we have to follow in order to achieve the protection, no matter where it's located. And of course, in some cases, different enclosures will also have what's called a Nema rating, or even in Europe, we talk about an IP code rating. Okay. And just so you know, the Nema ratings do not correlate directly with an IP rating. Okay. And we'll talk about that to give you kind of an overview on that. But they are unrelated. Most of the time in the U.S., we're going to do things with the Nema ratings. And don't let this confuse you with what you see in the code book in 110.28, because there you'll have your dry and wet location and 3 R's and things like that. Type 1 for dry location. Here we're talking about things that might have to do with explosion applications, okay? So, but I'll give you a better understanding of what we're talking about with all that thing. So let's define the classes so we know what constitutes a class 1, what constitutes a class 2, and what constitutes a class 3. Now, if you in your National Electrical Code, it's pretty easy to grasp this, because you're going to go to Article 500, and that's what it's designed to do. It's designed to tell you what each of these locations. But I'm just going to give you, again, the 30,000 foot view, rather than verbatim read it from the code book. So the most restrictive of all these locations is a class 1. Why is that? Well, it's an area where flammable vapors, gases may be present as part of the operation, part of the daily course of business. It could be present at any given time, okay? That is what we're talking about, all right? And so what other liquids? Are we talking about flammable gases? We're talking about flammable liquid-produced vapors or combustible liquids above their flash point. Okay, so if you have liquids that are flammable and they're at a location where they could have temperatures that could rise above their flash point, then that's a problem. That is a class 1 location. Now, what are some examples of a class 1 location for people that ask? Oil refineries, as we talked about, usually you're going to be dealing with flammable vapors there or gases or potential fluids that you could have a condition that could rise above their flash point. So that's oil refineries. And what about paint shops? Paint shops typically always will have a certain amount of vapor that is in the air. It's why you wear respirators when you paint. Okay, so last thing you want is an open flame or a spark or anything in those environments. So you're typically going to treat that area a little bit more riskier than you would somewhere else. So you're going to use explosion-proof enclosures, things like that. You're probably going to try to keep any make or break application out of those locations. And so paint shops are real prone to being a class 1, obviously class 1 division 1 locations. Oil rigs and the ones that are offshore. The ones that are offshore, the platforms, you have to be real careful. I think it wasn't not very long ago we had an explosion, and I think a movie came out about it, on a oil rig, and it is a constant class 1 location. Now, there's obviously other areas in there that are not class 1. There might be class 1 division 2, which we'll talk about in a minute. Or unclassified areas based on where they're located, whether or not there's ventilation or pressurization or something that takes it out of a hazardous location or a classified area. Okay, but most of the working meats and bones of a rig like that on an oil rig is probably going to be it's definitely going to be a class 1 because of the flammable vapors and gases that could be present. But again, liquids that could be present that could get above their flash point are things that you have to think about in those type of applications. Now, what about a class 2? Well, we were just talking about flammable vapors and gases, but now we're talking about areas where you have combustible dust. Now, combustible dust can be extremely hazardous if it gets into the air, okay? So once this gets out of the air, and what are we talking about? Well, coal mines generate a combustible dust into the air. Grain silos, because the constant grain being poured in and moved around, it creates this dust that gets into the air, and it can be very flammable. Hay storage, okay? When you get hay storage, you'll have dust that comes off of it that has enough material in that dust that if you put it together with that perfect triangle, and you have this spark, which is the ignition source, and then you have the oxidizer, which is typically oxygen, and now you've got the actual part that's the most critical when it comes to the dust is now you have this issue of, well, I've got everything involved in this little triangle that I'm worrying about. And so now I've got the flammable substance, which is the dust. So I've got everything perfect in this triangle of danger with this combustible dust. Okay, so class 2 is dealing with things like that. Anything that would have a potential for combustible dust. A coke facility, and not the coke you're thinking about, and not the coke that's made down in Georgia, but coke dust, things like that, all can be considered a combustible dust. Okay? The next thing is a Class 3. Now, Class 3 deals with ignitable fibers and flying debris that gets up into the air as part of the production process. Okay? What are we talking about? Well, paper mills, because of the production of paper, always has this little fine fibers and flyings in the air. That could be combustible. Obviously, in greater concentrations, that can be extremely combustible. All right, but it's ignitable is what we're worried about. That those the ability for all of that to get into the air, and it can be easily ignited. Okay, so that's our bigger concern with the Class 3 is the ignitable presence of these fibers. Okay, so paper mills, textile mills, woodworking facility could put these fibers or flyings that are ignitable. So we have flammable vapors, and I probably shouldn't have said combustible fibers earlier. I'm going to clarify it now. Class 1 is flammable vapors and gases. Class 2 is combustible type dust. And then Class 3 is more ignitable fibers and flyings. So I can kind of keep that. Again, I'm just going from the cuff here, trying to give you some information in the podcast. So bear with me there. I'm not perfect like some other people are out there, I guess. So the next thing we look at is, now that we know the classes, we got to look at the difference of the frequency. I mean, is it going to be present all the time? Is it only there when it's under storage? So now we have to understand that when we're still doing an area classification, now we move into two different areas. We're going to move into, or I should say, a second area, and that is divisions. Now, mainly what we use in the United States is divisions, and that's what the National Electrical Code has had for years, okay, is the divisions. Division 1, Division 2. Division 1, more severe than Division 2. Both of which are hazardous locations. Both have their own rules. And so, but we also have zones. And the zones are given to us in 505. And the zones, as I said earlier on, are broken down in 0, 1, and 2. And then for combustible dust, it's 20, 21, and 22. Essentially the same thing, except the zones are broken down into three categories, or three of them, rather than just two in the Division 1, Division 2. There's three for zones. Now, zones are broken down, because of the way it's broken down, more details get driven than the divisions would be, okay? And when I say that, the zones even break it down even more into the different classifications for gases and dusts within those zones, okay? So that you know whether or not you're dealing with the zone 0, zone 1, and that type of thing. So if you're looking for detail, then zones are there. Okay. Now, currently, you're allowed to use the division method or zones, however you want to use it. Okay. Now, let's talk about Division 1. What's the criticalness of Division 1? Now, it doesn't matter when you're in the Class 1, so it's flammable liquids or vapors, or you're in a Class 2 combustible dust. You're going to have, and we'll kind of leave Class 3 sitting alone down here, the flyings and fibers, things like that. Okay. Right now, we're going to talk about the two more volatile ones, and that's the vapors and liquids for flammable, and then, of course, the combustible dust. Now, Division 1. Division 1 is a hazardous or ignitable substances are present or expected to be present for long periods of time under normal operating conditions. I mean, it's part of either the production, part of the facility. This substance is expected to be there. It's just part of the production process. So you can't get rid of it. So if that's the case, that would be a Division 1. Whether you're dealing in Class 1 or Class 2, that's a Division 1. Okay? Now, with that said, let's circle back around to a Class 3, because I don't want to give the impression that we don't have an issue with Class 3. There is. Okay? So we do have a Division 1 and Division 2 as well for Class 3. For the ignitable fibers and flyings, okay? So it's just, usually that is a smaller one, a smaller topic, and it's not as critical in discussing that one. Because of brevity, we're going to deal with the two that we deal with, again, more, and that's the flammable liquids and vapors and combustible dust. Okay, so back to the topic. So, Division 1, the potential of the actual presence of this hazardous or ignitable substance is always there. It's expected to be there. It could be part of the process. Okay, so that's Division 1. So if it's flammable gas or flammable vapors that are there as part of the production, maybe a byproduct or part of the production, then that's a Class 1 Division 1. If combustible dust was the same situation, as part of the production, it's there all the time, expected to be present for a long period of time under normal operating conditions, it's just part of the production, then that's a Class 2 Division 1. Okay? Now, you're trailing with me. So now let's move to Division 2. Well, Division 2 is still a hazardous classified location. It's just the hazard or ignitable substances are only present there if there's an abnormal condition takes place, like something leaks. Okay? And usually when that happens, it leaks and you shut something down, or there's some other type of mechanism that can tell you that it's leaking, and you can put things in safe order. But it's not there under normal conditions. It's an abnormal condition that does this. Okay? And again, a good example of that is leaking or storage containers that might be there. The storage containers might have material in it that if it was open and the vapors and everything got out all the time, or these vats were open, maybe part of production, then that'd be a Class 1 Division 1. But they're stored in containers. The only way it would get out is if it leaked and things like that, then typically that's what you're going to see in a Class 1 Division 2 location. And again, same kind of concept for Class 2 for combustible dust as well. Same thing. Only gets out under an abnormal condition. All right. Now, pretty simple, right? If it's there all the time and it meets the hazardous and ignitable substance, then, and again, there's a group of them, and we'll talk about those in a minute, the different groups of different substances. But if it's there all the time and it's a Class 1 Division 1, if it's a vapor or gas, if it's a combustible dust and it's there all the time as part of production, then it's going to be Class 2 Division 1. If it only can happen, or it's storage of these of chemicals and things like that, and it can only happen under a rupture or a leak or a malfunction, then it would be a Class 1 Division 2 if it was liquids or vapors, or if it was a combustible dust, Class 2 Division 2. You with me? All right. So the next thing we'll talk about is zones. Now, zones are a little newer. They came about in probably the latter part of the 90s, and people started using them. North America kind of caught on to it, so there's a lot of locations, especially like down in Houston, that actually believe in the zones because it is more detailed in the zones. The manufacturers of equipment for the zone applications, even though they're not generally... you couldn't equate a zone to a division. Most manufacturers want to put now a division classification on it as well as a zone, so you kind of get an understanding on which one you're working with. But that came around in about the late 90s, early 2000s, and it started to pick up. But to be honest with you, the zone concept in North America is really based on those international standards, okay? The IEC and APEX and things like that. Kind of really based on that. So let's kind of give it an overview and kind of tell you where we are in this whole scheme of everything. So let's talk about flammable material. Now, if I'm dealing with flammable material, gases or vapors or liquids above a flash point, things like that can get above a certain flash point, then if they're present all the time under the IEC standard, okay, if they're present all the time when we use a zone method, then it would be zone 0. Okay, it's always continuously present, kind of like what we just did in Division 1. No different. Okay, under the National Electrical Codes, Article 500. No different. And also that mirrors what it says in Article 505 for the NEC, because that is your zone category. Now, that came from the European standards brought into the National Electrical Code. Okay, so if it's present all the time, then again, that's going to be zone 0 for the IEC standards. And in the National Electrical Code under NEC 505, that's going to be also zone 0. Okay, matches it perfectly. Under Article 500, though, for use in 501, 502, 503, 504, then that's going to be just your flat, obviously, Division 1. Okay. Now, if you have an application where it's not continuous, but it does get present intermittently throughout the day, a condition can take place where it is a known thing to happen on a intermittent basis, not because of abnormalities, but because at some point it will be present, not long term, but will be present in the zone system. We call that zone 1. Now, under NEC 505, which is a zone system in the NEC, National Electrical Code, that's zone 1 as well. So it's mirroring the IEC standard. But again, in Article 500, what we're used to for the division classifications, that's still going to follow under Division 1, okay? Because it's still present part of the normal application, or it's expected, okay? Even though it's intermittent, it's still expected. So as you can see, the different classifications, Division 1 is very broad, whereas you might have a piece of equipment that is less stringent in the Zone 1 than a Zone 0 would be. So somebody might say, well, look, I'm going to go to the zone classifications rather than the division classifications. Again, most of the equipment out there for hazardous locations probably going to have both a zone and division by now, but you might design something and you need to play off this. Okay, both are acceptable in the National Electrical Code. Most people that I deal with still use the division. All right, and so then what about those abnormalities? Well, again, as you can expect, in the IEC, that would be Zone 2. It's only present if there's a rupture, a leak, storage, could cause a container to rupture or an accident, then that would be Zone 2. And then with the 505 in the NEC, which is, again, dealing with the zones, is going to be Zone 2 as well. And, of course, you probably guessed it, Article 500, this is going to be a Division 2. Again, only there if it's everything's okay, but it could rupture or leak. So we want to have that level of protection there. We'll label it a Division 2, hoping it never happens, but we'll label it a Division 2. Or if you're using the zone method, we'll label it a Zone 2. Okay? All right. And in Canada, they also Annex J for the Canadian Code. They also follow the zones in Section 18 of the Canadian Code, but they also have an Annex J, which kind of mirrors what we do in Article 500 of the NEC. They have a Division 1 and Division 2. Okay, so that is something that they have in their standards as well. Okay. Now, when we're talking about combustible dust, you know, it's pretty much the same thing. We're rehashing the same information. If it's present continuously, it's going to be Zone 20 under the IEC, or as well as US NEC 505. So that's Zone 20. So the only difference to remember is gas is only a single number, and combustible dust, it throws an additional 2 in front of it. Okay, so the zones stay the same; it just throws a 2 in front of it. So if it's present all the time, it's combustible dust. It'd still be a Division 1 under the National Electrical Code's Article 500. But under NEC 505, it would be a Zone 20. And under the IEC, it's Zone 20. And then if it's present intermittently, just like we said with the flammable gases and liquids, then it's only there sporadically, but we know it's going to happen. I mean, it's part of the production. We know that it's going to take place. Well, if that's the case, then it is present, part of the general use, but it would be a Zone 21. So you just add that 2 in front of the 1. So it's kind of easy to remember zoning, how to do that. And of course, abnormal condition where something's not supposed to, it's in containers or it's in pipes and it's not supposed to be an issue or ever be an issue of rupture or things like that. Or if it ever did rupture, then we're going to call it a Zone 22. Whether it's in the NEC 505 or the IEC, we'll call that Zone 22. Again, it's in containers that somebody could damage and leak, and then you have a increased risk. Then that's going to be where we get the Zone 22. In the National Electrical Code under Article 500, for example, where we have the classes and divisions, then it's going to be Class 2 when we're dealing about those abnormal present locations where it's abnormal condition to have those combustible dusts associated with it. Okay? All right. Now, the next thing we want to move into is the groups. Because on every label that you look at, you're going to see not only whether or not it's Class 1 Division 1, Class 1 Division 2, Zone 0, Zone 1. You're also going to need to look at the type of group. And the group is the type of flammable material, okay, or combustible material, or easily ignitable material, or you're looking for that type of information. Okay. Now these are usually pulled out of NEC Article 500, and there's a list of groups in there: Group A, Group B, C, D, for example. And Group A, for example, would be acetylene or acetylene, however you want to say it. Group B would be things like hydrogen, ethylene oxide, propylene oxide, things like that. Group C would be ethylene, ethyl ether, and then of course Group D would be things like propane, acetone, ammonia, butane, natural gas, regular gasoline, methanol, all that kind of thing. So on your label, you'll have different groups. So not only do you look for a piece of equipment that shows you that it can be used in a Class 1 Division 1 or Class 1 Division 2, but you also need to look at what type of volatile material, if you will, is this piece of equipment is going to be used for. Okay, if it's in a location that has ethylene oxide, for example, then you need to make sure that it has a Group B marking on that label of that piece of equipment, because that's where you're planning on putting that piece of equipment. So not only do you know the class and division or the zone, but you have to pay attention to the group type of the material that you're going to be putting this piece of equipment in. Okay, now beyond that, when you start looking at zones, for example, in 505, we have additional group classifications. For example, Group 2C, and we're not saying the number 2. These are like a Roman numeral 2. It's Group 2C, which is acetylene. You have a Group 2B plus H2, and that's hydrogen. A Group 2B for ethylene. Group 2A for propane. Group I, or 1, or however that symbol is, then that would be methane. So I like to think of them as Roman numerals. Somebody will tell me it's I, but to me it looks like Group 1 because the other groups are A's, so then these are numbers, and I usually say they're like Roman numbers. Group 1 or whatever is methane. Okay, so anyway, under the zone method, you have those groups as well. Okay, now the next thing that we have to look at on the labels is you have to remember that where we're going to stick something, we need to look at the temperature class. Why? Because the maximum ambient surface temperature of the piece of equipment or the device or whatever it is, if the surface temperature can reach a certain temperature, and let's say it's in combustible dust, and combustible dust settles on this equipment, if the surface temperature gets up to a certain point, then that surface temperature could rise a temperature to auto ignition. So we have to be very careful of that. Okay? So we have to look for that. Now, various things happen with internal temperatures that can rise. So what you'll usually have on equipment is what we call a T rating. It'll be like T1 is 450 degrees Celsius, T3 will 200 degrees Celsius, T4 is 135 degrees Celsius, on down the line. Okay? Now, that's the temperature ratings of the surface, because the last thing you want is put a piece of equipment or a device in an environment where it internally could heat up, okay? And as it internally heats up, the actual ambient surface temperature for that device can reach a volatile level, and we don't want that, okay? So that's what we're worried about, the temperature classes. Now, if you're used to dealing with this stuff, you're used to dealing with this hazardous locations and motors, you might even see something even more detailed, which might say something like a T2A, T2B, T2C. And those classifications of that nomenclature gets even deeper into the ratings or the temperatures that are involved. Now, if you're wondering what that means, and all those temperatures and temperature classes and T codes, then you can go to the National Electrical Code, and there's a table 500.8c, which talks about the maximum temperature, and then it gives you the temperature class on the right. And that's really important to understand that, because you have different things like temperatures that you can't exceed for auto ignition temps and all those type of things. So it's really important for you that work in that to make sure that you have a temperature class that is accurate, okay? And it can vary based on the internal heating elements of a specific device. So you have to be extremely aware of that. The good news is, in 500, there's a really, really, really good explanation when you're dealing in and I think I've got my code book. Now I'm in the 2020. I'm looking in the 2020. It's 500.8 equipment, and you go down and you'll see a bunch of information. It looks like C4 deals with equipment temperatures and things like that. So really good information on temperatures for you to look at. All right, so the next thing we'll move into is protection. So we've covered temperature, surface temperature, again, internal components. We talked about the groups, which incidentally I only talked about A, B, C, and D, but you do need to know that it keeps on going. You get into other applications when you're dealing with the class 2 group classification, then there's an E and an F and a G. So you do have additional, different groups that you get into. Those are class 2 groups, and the ones that A through D I generally talked about, that's what's called a class 1 group. And their explanation of each one are in the National Electrical Code, and that starts on 500.6a. Okay? And again, I'm talking in the 2020 National Electrical Code, but I'm sure it's no different in the 2017 code. All right, now, how do we protect things? How do we protect people? How do we protect equipment? How do we contain things? And we're looking at protection concepts, or what we can do to protect things. Now, protection concepts can fall in a bunch of different categories, but one thing's to remember, look, one way to do that is if we don't have an arc or spark and we don't create hot surfaces, okay, because we pay attention to the temperature ratings of the equipment. If we don't do these things, then we create a safer environment, we increase the safety, and we create something that's called non-incentive, okay? Because there is nothing there to complete that triangle. There's no way we can have ignition if there's absolutely no arc and there's no spark, and we keep the hot surfaces, whether we keep it away from anything that could cause combustion, or it's just it's designed that way and it doesn't create a hot surface, so we pay attention to those T codes. If we do that, then we increase safety. Okay, so that's one way to make a safe condition, is just don't put the arcs or the sparks. Don't give it one part of that explosion triangle, if you will. Okay, remove that, and however you do it based on equipment, design, there's other ways to do it. We could take some switching components that might be immersed, for example, in oil, and things like that, so that there's no real arc that anything can get to. There's certain ways that you can do that. Okay, so manufacturers have equipment that can do this. So that's one way to increase protection, through some type of mechanism that just will not produce an arc, a spark, or create hot surfaces. Okay, the next way is thinking about protection concepts is containing the explosion. So we're talking about explosion-proof enclosures. We're talking about flame-proof enclosures, or even some that are called powder-filled. Okay, so that really reduces annular space within the actual enclosure itself. So explosion-proof. Now, here's a couple things to think about here. It doesn't mean an explosion couldn't happen. It just means that it's protecting you outside of this enclosure because it contains the explosion within itself. Okay, and so it has a rating for that. And so that's why you got to pay so much attention on the seals and things like that, seal within 18 inches and things like that, because you really are trying to isolate the potential explosion inside of this explosion proof. But again, it could be an explosion proof, it could be flame proof, it could be powder filled. There's other different ways to contain the explosion. And if there is a fire within it, it's a way to extinguish the flame. Okay, that doesn't mean it's not going to happen in it. There's just a way to contain it or extinguish it within itself. Okay, now that's one way of protecting. Okay, the other way to do this is, how about just limiting the energy to the space, or limiting that surface temperature itself? Okay, how do we do that? Well, through things like intrinsically safe apparatuses. Okay, things that it's just not going to let enough energy get to a certain point where it has enough energy to even create a spark. It's very low voltage, very low current. It doesn't have the ability to generate enough energy to get something to an auto ignition temperature, or if it's to create what's called a spontaneous incident. It just doesn't have enough energy. And that's what intrinsically safe means. It's just not enough there. It serves its function, it does its thing, but it's just not enough oomph, if you will, in order. So you're limiting the amount of energy. Okay, whether it's in an enclosure and in an environment, it's intrinsically safe. Whether it's conductors, cables running through the environment, it's just not enough there. Okay, so that's limiting the energy. So that's a way to protect your concept. And the code deals with applications for intrinsically safe applications, right? So that's one way to do it if that's an option. Now, one of the last ones that I talk about is, how about breaking up that triangle altogether? So we did keep the arc away, the spark away, but maybe you can't help but have an arc or spark or something in this location, but you can keep the flammable material away from it, or you can encapsulate it, or you can oil immersion into it, or something like that, okay? Maybe you protect it within an enclosure combined with something else that will keep the flammable material out. Now, one very well-known way to do this is through positive pressurization. Okay, so I have a room, for example, and it's constantly pushing pressure out, so nothing can get in because it's positive pressure out. Things like that. Encapsulation of switches, relays, things like that in these volatile environments can remove the ability for the flammable material to either get in or get out of the environment, right? So kind of some of those things to think about when you're developing your protection concept. And we talk about that in the code. There's reasons why we seal things off, reasons why we use explosion-proof fittings, and all these type of things depending on the environment we're working in. And so that's kind of the things to think about. Now, we've kind of moved on through this pretty quick, but let's talk about the common Nema and the IP codes. Now, one thing to remember is that Nema, and I used to work for Nema doesn't manufacture anything. Okay, Nema doesn't test anything. So when you see something that has a Nema rating, the manufacturers put out a collective agreed upon standard, and it gets adopted into a standard. I shouldn't say adopted. It gets put into a standard that people can utilize, manufacturers utilize it in order to be able to say that their product has a Nema rating. So whether it's devices, Nema rating, you construct it to a certain set of rules, a certain way, and you're allowed to put this Nema rating on it. Same thing with enclosures. So there's a varying types of enclosures that you're going to find in National Electrical Code, and you get a nice little list of all those. If you go into the National Electrical Code and you go to table 110.28, you're going to see a nice little list, and it's going to talk about type 3, type 3R, type 3S, type 3X, 1, 2, 3, 4 if you have indoor locations. And then, of course, it has your outdoor locations. Example would be 3R. Those are some applications, and you can go to the NEC and see what those are. Nema doesn't certify any of that. Okay? They come up with the standard based on manufacturers, and it has test requirements. And if a manufacturer wants to make an enclosure and they want to put a certain rating on it, then for a certain condition of use, then they do it and they follow all the rules and all the tests, kind of a self-certification, if you will. Now, heaven forbid something goes wrong and they get put under the gun and somebody gets tested and they put some kind of listing on their product or classed it or typed it, and then it really didn't and it failed. Okay, that would be a bad news for them. So as long as they construct it in accordance with this standard that's put out by Nema, then they can put this type listing on the enclosure, okay? So generally that's what's accepted in North America. Now, over in Europe and even in some places in the U.S., they'll still accept what's called the IP, and that's called the Ingress Protection Code, okay? And it's just referred to as IP code. And really, people accept that all over the world. Now, they don't necessarily equate. You follow me? So a Nema 4 doesn't necessarily equate to any specific IP4, okay? It has a different numbering system, and in some cases, the IPs or the ingress protection gets even more detailed in what, if you have an enclosure that's listed as an IP, then it can have a lot more details in what it is, whether it's a certain amount of pressure of spray, things like that for its classification or its use. Then, they're not exactly the same, okay? So key thing to remember, just because something's NEMA rated doesn't mean it's a specific IP rating. Now, it might have an IP class that covers it, but you got to make sure. Now, one thing is true is that both NEMA types and the IP codes, both of those indicate physical protections against water and material ingress. And ingress means ingressing and getting into the enclosure. Okay, so both do cover that. Okay, that's not the issue. NEMA covers that. There's various tests, different types for that, and tests that have to take place under the enclosure standard for NEMA is enclosure document 250. Okay, not to be confused with 250 grounding and bonding in the NEC. This is a NEMA standard, so it's a NEMA 250 enclosures document. I think it costs about $110 for you to buy that. And it tells you all the tests in order to achieve each one of those types under the NEMA. And the manufacturers of enclosures get this document and they make sure they do all the tests that are listed there. And they can use that rating. And then us as a consumer know when we have a certain environment, a certain condition, that this enclosure is going to be fine. Like outdoor location for rain, NEMA 3R. We know that the manufacturer had to test it to that. Okay? But they're not harmonized. So the NEC does not harmonize with the IP. Two different things. There's no cross-reference of each that you can just look to and say, oh, well, this matches this 100%. No. You've got to really check them out, okay? So what is the most predominant one done is obviously NEMA, and usually it's protection against water and corrosion. So corrosion, you'll see a NEMA type with an X attached to it. Or for rain, for example, would be a 3R. But the difference is most of the classes for protection for NEMA are for against water or ingress of water. And then, of course, they deal with corrosion. Okay. Now, under NEMA, since we're talking hazardous locations, okay, then we're talking about NEMA classifications types 7, 8, 9, and 10 generally, okay, which is some additional NEMA classes that are included in for hazardous location protection as well, okay? So let's kind of give this a look and see how you can see the difference. Okay, so let's say I go out and, I don't know, let's just use an example. Let's say I go out and buy a NEMA 4. Now, the NEMA 4 says it's for indoor-outdoor use, protection to personnel against the access to hazardous parts. So it's designed so people can't just poke things through it. Okay, so it has that protection against getting to hazardous parts. Okay, it has protection against solid foreign objects. What does that mean? Well, things like dirt falling in it, blown dust, things like that. Objects in the air that you physically have to move into it. Okay, it also has protection from ice and hose-directed water under normal pressure of like a water hose, okay? So all of these things are part of the test that a manufacturer has to do in order to slap it with a NEMA 4 rating. It's nothing that NEMA tests, okay? That's a fallacy people think. NEMA tests nothing at all, okay? They sell standards, but they test nothing. They might develop them with the help of ANSI and other bodies, but they don't test anything. Now, what about a NEMA 4X, okay? So a NEMA 4X is very similar to a NEMA 4. However, it has the addition, because of that X, it has the addition of corrosion protection. So if I need corrosion protection added to my NEMA 4 in this location because of some listing or some engineer specification or the environment that's going to be at that might be a corrosive environment, then I would bump it up, for example, to a NEMA 4X. One good example of this might be, let's say I'm installing a NEMA 4 down near the ocean, and I'm worried about corrosion, and an engineer might spec that instead of a NEMA 4, and it needs a little bit more than a NEMA 3 or 3R, so they might go with the NEMA 4X. It gives you all the benefits of a NEMA 4, but it also gives you the benefit of corrosion resistance. Now, when we look at a NEMA 4, it's real important to understand that what are we trying to do to get an equivalent IP or ingress protection rating? Well, there's an IP55, so these can be what's called stackable. You have an IP55, which is protection against dust and liquids such as water jets. Then there's an IP65, which says it's dust tight and protected against water jets. And then you have an IP66 that says it's dust tight, It is protected against powerful water jets. Okay, again, the difference in the 65 and 66 is powerful water jets. So obviously in the tests they do, it's much more pressure behind it that could push it into this enclosure and potentially get in the crevices or something like that into the enclosure. So it's a little higher rating. So as you see, it's stackable. You have one that's 55, that's dust and liquid, such as water jets. And then you have 65, which is dust tight. A little difference than protection just against dust. It's actually dust tight and against water jets. And then you get into the extreme of IP66, which is dust tight and protection against powerful water jets and high seas. Okay, so it throws that one on there, high seas. So depending on the location and the classification, you might be using Nema. But as long as you know what the IP ratings are, you can look for the enclosure that also might have an IP rating that will also meet the need of whatever you're dealing with based on the environment. Okay, so that's kind of how they work in conjunction with each other. Okay. Now, I guess I should tell you, if you're in the National Electrical Code and you're looking at Table 110.28, I get people that ask me all the time, says, where do I get these IP marks? This seems like the IP ones are way more expansive, and manufacturers have a lot more to worry about with the IP than just the kind of basic NEMA 4, NEMA 4X, things like that. NEMA 3SX, which is stainless steel. I mean, think about it. So you can find all these IPs, and you're probably going to have to buy it. Okay, and that is an ANSI IEC 60529, and it's titled Degrees of Protection Provided by Enclosures. Now, the code also lets us know, and that's an informational note to that table 110.28. It also says, and it's really important, it says IP ratings are not a substitute for an enclosure type rating. So, as far as the National Electrical Code goes, you have to meet the NEMA ratings. That's what's in this table. The IP ratings aren't a substitute. They might add on, build upon. You might get a NEMA rating for a manufacturer does an enclosure, and they give you this NEMA rating to meet the need in this table. And you look at this table, it'll tell you all these conditions, like falling dirt, incidental contact with enclosed equipment. You pick a piece of a type of enclosure here, but you also might get added benefit from an IP rating as well. And you can go to that document in the ANSI IEC for that, but they can't take the place of what's in here. Okay? So just kind of covering all that. Now, markings. What kind of markings will you see? Well, like I said, you might see a UL mark with a C for Canada and a US for US. Okay? That is where they have a interrelationship between the two standard bodies. You might see FM with like they have it's kind of like a diamond, if you will. I guess they're a triangle, or I guess it's a offset square, whatever it is. That's it could have approved under it. It could have just the FM. If it's their one for use in Canada and US, it might have approved and the FM mark with a C and a US under it. Canada might have the R symbol, might have just CSA, might have CSA C with the US. Same thing for UL. You might have the ATEX. If it's explosion proof, you'll see something with looks like a hexagon with an EX in it. If it's an IEC standard, it might be a little box that has IEC in it. If it's an explosion proof, it might have a little nomenclature beside it that says EX. All these different types of markings you can look for on the labels itself or whatever the equipment you're working on. Now, with that said, let's talk about explosion-proof labels. There is so much information that you could get on an explosion-proof label. It might tell you on that label the NEMA and the IP ratings. It might tell you the classifications, whether it's Class 1 Division 1, Class 1 Division 2, Class 2 Division 1. But when it does that, it's also going to give you the groups, Group B, C, and D. If you're in a Class 1 Division 1, it'll tell you what groups you can use this piece of equipment in. And like you said, it might be in acetylene, it might be in butane, whatever it is, it's going to tell you the group that's on it, okay? It's also going to tell you the temperature ratings, the temperature codes, the allowable ambient temperature, okay? Usually is the nomenclature for that is usually a TA. So it's going to tell you where this piece of equipment can be utilized, say minus 40 degrees Celsius to a plus 65 degrees Celsius. It's going to give you a window, okay, that you're working in. So all that stuff is there on the actual nameplate. It might have, to be honest with you, it might even have FM, CSA, and UL. It might even have ATEX certified on it. It might even have ATEX with a little symbol for explosion proof. All of those things might be located on this label. One thing it's going to have is it's going to tell you the equipment group that you're working in. And if we're dealing with the IEC standard, it might be an equipment group 2, for example. And then that'll be like a Roman numeral 2. And then, of course, it might give you the equipment category. And then it's going to tell you whether it's the environment is good for gas or dust and things like that. Whereas over underneath the side for the FM or CSA, it might give you other things, like it might say EX for explosion proof, and it'll tell you which classes that could be, class 1, zone 1, and 2. All these type of things will be on this label. If it's an enclosure itself, and this piece of equipment this label encompasses not only the enclosure but internal apparatus, then it also might have an IP rating on it. If it's a European standard, it might say that it's IP68 in it. But it also might say that it's also an enclosure type 4X, okay? Because if you're using it in the U.S., then the type that's listed in the National Electrical Code under 110.28 has to take precedent. And so the additional IP code is just additional, okay? And it does give you some additional clarification. There'll also be warning labels most of the time on there that'll tell you do not open in an explosive environment. It'll tell you install the conduit seals within 18 inches of this enclosure. It will give you other additional information. Okay, so all of that's typically, and the manufacturers have gotten really good about putting that type of information on a label. Now, if you have a piece of equipment that has a label on it and it's for intrinsically safe label, then you're going to kind of get some of the same type of things. You're going to get the maximum loop voltage, might say 30 volts. The maximum loop current, which would be 30 milliamps, for example. It will tell you the class, whether you can use it in a class 1, division 1, and it'll also give you the different types of gas groups like A, B, C, and D. But then when it comes with class 2, division 1, it might give you the different types of dust locations, and those typically are going to be dust groups E, F, G, things like that. It'll all be listed on here, okay? It'll also give you the T codes as well. All of this stuff will be on here. So you're going to see this about the same material for the same locations, and it's going to tell you where it's suitable to use. The key thing about the intrinsically safe is that you know that it doesn't have the ability to generate enough energy to cause a fire, because it's not going to give enough to have one level of that triangle, which is the source of ignition. Okay. The other thing you might see from time to time, and I just wanted to throw this out there, is you might see the CE compliant mark on a label or a piece of equipment. Remember, that's a European conformity standard. That has nothing to do with anything safety. It's not the same as the FM approvals, CSA, UL, things like that. It is not the same. So just because you see CE, that is not a safety mark. That's a conformity mark for the European standard. Okay? That has nothing to do with safety. All right? Okay. So to summarize, what we talked about was why we classify these locations, hazardous locations. We talked about how to define those hazardous locations. We briefly talked about the classifications. We went over area. We went over class. We went over zones. We went over divisions. We talked about the markings and the specifications and the different standards. We even talked about the methods of protection. Okay, whether or not it's pressurization, whether or not we remove the source of the arc, or whether or not we remove the flammable material by enclosing it in a certain location or separating it from the condition. All those things as part of a protectiveness, or maybe even the use of explosion-proof enclosures, which are designed to not stop the explosion, but to contain the explosion. So later what we're going to do is we're going to talk about things like seals and why they're important, but we're not going to do that today because that just is, I don't know how long we've gone in this podcast. I guess it's an hour and 20 minutes, but we're going to save that for another one. Hopefully you're excited about it. Give me some feedback. Let me know if you want to hear about seals, and this is your building block. Then we'll move into seals and talk about where seals go, whether they have to be listed seals, whether or not they can just be like filling a conduit with some kind of foam, all those type of things. We'll cover all that, but we'll just move from one thing to another. So hopefully you got something out of this podcast. Until next time, folks, stay safe and God bless.
Every day the future's getting closer. Every day the future's looking bright. Every day is another beginning.